So this is electrostatics continued. They touch, they get the same charge, charging by conduction. They don't touch, this becomes polarized. And then if I ground it, the electrons are able to leave. And so now charged by induction, now they end up having the opposite charge. Coulomb's law, come on now, we all know that. Q1, Q2 over R squared. You know, if the distance between the two objects changes, just remember that there's an R squared involved. Elementary charge, that's either one proton or one electron. On the front, they tell you it's 1.6 times 10 to the negative 19th coulombs. Coulomb is the SI unit of charge, capital C. Electric field. Electric field is the area, or the volume, I should say, around a charged object. I have this electric field. And the electric field lines are what a positive test charge wants to do. So in this case, the positive test charge wants to get the hell out of Dodge. They're going to have 5 or more. They're going to touch the source. In this case, the arrows are going to point away, evenly distributed. And we know that the strength of it is E is equal to F over Q. And while we're at it, how about those equipotential lines? Equipotential lines in this case is going to be a place, it's always perpendicular to the field line, right? These guys are always perpendicular to the field line. And this is where the voltage is going to be constant. So maybe there's a voltage everywhere on this line, it's going to be 10 volts. And then there'd be another one out here someplace where maybe it would be 5 volts, right? So every place on this second would be 5 volts. Equipotential lines. Moving on. So now we start getting into electric current a little bit. I guess that's it for electrostatics. What else in electrostatics? As far as vocab goes, that's kind of it. In general, electrostatics, remember that in between parallel plates, not only does the E field look like this, but it's uniform. It's the same everywhere. The voltage is different, right? This is where we get this formula. What is it? V is equal to E over Q, where this is the energy or the work. But now moving into electric current, we talked about this before. It's IQ over T measured in amps. Conventional current, we don't need to know about that. So I'm just gonna, a battery, well, we know what that is, what causes a potential difference. Electric circuit, we know what that is. Ampere, those are the units. Resistance, we get a resistor, right? And V is equal to IR. By the way, resistance in a wire is resistivity times the length divided by this. Remember that when the wire gets hot, then the resistance goes up. It becomes worse of a conductor when it gets hot. How do you remember that? Superconductors are cold. So there are these things that when you get close to, I don't know, I don't think it's all the way to absolute zero, but when you get to like negative 200 degrees, the resistance goes to essentially zero. So that, although superconductors are not a topic for the Regents, we need to know that when a wire gets hot, the current slows down because the resistance goes up. Here's a resistor. This is this symbol where it's a resistor symbol and an arrow. That's a variable resistor or potentiometer. And that's the dimmer switch, if you have a dimmer switch to control the lights in your room. Resistor, parallel connection versus series. Series always has one path, right? And in order to find the current, we have to add those two resistors together. And a parallel connection has multiple paths for the current, and so each branch is going to have its own current, and the voltage in each branch is going to be the same as the battery. Where here, the voltage drop across R1 is V1, and the voltage drop across the second one is V2, and V1 plus V2 would equal the voltage drop across the battery. All right, so let's just go and finish this out. Some vocabulary about atomic physics, and it's at the end. That's the end of this. So alpha particle, remember what an alpha particle is. Alpha particle is basically a helium nucleus. It's 2 protons and 2 neutrons. It's the alpha particle. There's the symbol for alpha there, alpha decay, right? Nucleus, that's what's in the middle. And then remember, so what are the other types of radiation? There's beta decay. So beta decay is when it gives off either a negative electron plus a neutrino, or it gives off an anti-electron, positive, and then it would be an anti-neutrino. And this is beta decay, and this is associated with the weak nuclear force. And then alpha decay and the nucleus, all this is the strong nuclear force. And it's not listed here, but quarks, right? Quarks, protons, and neutrons, they have 3 quarks inside, and that's also the strong nuclear force. Energy levels. So that's the deal where you look on the reference table, right, and you have the n equals 1, and then way up here is n equals 2, and n equals 3, and when the electrons drop, then they give off a photon according to E is equal to HF. And absorption spectrum, we don't need to know that word so much, but when the light is coming in, I'll do it in purple highlighter here. When the light's coming in, there's certain frequencies that cause the electrons to, let's do it in red, that cause the electrons to jump up to the excited state. So yeah, just a quick rundown of some of the vocab that I thought was important.